Okay, this is Unit 6, Physical Behavior of Matter. This is a review for the unit exam. I'm going to try to do this review in two parts, only because I've tried to record several times and something's happening, so I'm thinking that I'm going over my time limit. So please, this will be part 1. Look for part 2. Energy is the capacity to do work, or the ability of matter to do work. You need to know the difference between kinetic energy and potential energy. Kinetic energy is energy of motion, and potential energy is energy that is stored. You also need to know the definition of temperature, the measure of the average kinetic energy of a substance's particles. A change in temperature means a change in kinetic energy. If I increase the temperature, particles will move faster, collide more, thus increasing their kinetic energy. If I decrease the temperature, it means particles will slow down, come closer together, collide less, and decrease the kinetic energy. Kinetic energy does not depend on the size of a sample. Absolute zero is the temperature at which all particle motion ceases. This is either negative 273 degrees Celsius or 0 degrees Kelvin. You also need to know the freezing and melting point of water, which is 0 degrees Celsius or 273 Kelvin, and the boiling point of water, which is 100 degrees Celsius or 373 Kelvin. There's a direct correlation between Celsius and Kelvin scales. A change of 1 degree Celsius is the same as a change of 1 degree Kelvin. Note that water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. That's a difference of 100 increments. On the Kelvin scale, water freezes at 273 and boils at 373, also a difference of 100 increments. You need to be able to calculate temperature in either Kelvin or Celsius based on what you're given in the problem. Table T gives us the formula for solving for Kelvin, Celsius plus 273. So in this example, what Kelvin temperature is equivalent to 35 degrees Celsius? You simply take your Celsius temperature, 35 plus 273, and get 308. Now, if I'm solving for Celsius, I'd need to subtract 273 from both sides, and I'd get Celsius equals Kelvin minus 273. So, let's review what we just learned. Which change in temperature of a 1 gram sample of water would cause the greatest increase in the average kinetic energy of its molecules? First of all, if I want the end result to be an increase in the average kinetic energy, then I must increase the temperature. So choices 2 and 4 can automatically be eliminated. So between 1 and 3, the higher temperature, of course, the particles are going to be moving faster and therefore have the greatest average kinetic energy. When the temperature is 300 Kelvin, what is the temperature in degrees Celsius? As I said before, we need to manipulate the equation. So Celsius equals Kelvin minus 273. So 300 minus 273 is 27 Kelvin. Another example, if something has a temperature of 5 Kelvin, what is this in Celsius? Again, Celsius equals Kelvin minus 273. So 5 minus 273 is negative 268. Notice it is possible to have a negative Celsius value, but never a negative Kelvin value. This is the main reason that chemists use the Kelvin scale. A sample is heated and rises in temperature by 12 degrees Celsius. What is this temperature difference in Kelvin? I already reviewed the fact that a change in 1 degree Celsius is the same as a change in 1 degree Kelvin. Therefore, if I'm raising and changing a temperature by 12 degrees Celsius, then the difference is the same for the Kelvin scale. Heat is a transfer of energy from a material at a higher temperature to one at a lower temperature. Imagine hot coffee in a mug. The hot coffee particles have a high kinetic energy and collide with one another. And they also collide with the container of the wall. And they transfer their energy to the wall of the mug, which then transfers it to the surroundings. So heat transfers from a body of higher temperature to a body of lower temperature. When comparing heat and temperature, we need to know the difference. They both are involved with kinetic energy. Temperature is the average kinetic energy of the particles in a substance, measured directly in either Kelvin or Celsius, and it doesn't depend on the sample size. Heat, however, is a measure of the transfer of kinetic energy, and we'd measure this indirectly by measuring in joules or kilojoules. And the sample size does matter. The larger the sample, the bigger the energy transfer. If we look at a Venn diagram, we can see that the two have in common kinetic energy. Heat measures the transfer of kinetic energy, while temperature is the measure of the average kinetic energy. When an ice pack is applied to a bruised arm, heat transfers from, as we said, body of higher temperature to lower temperature. So therefore it would be from the arm to the ice pack. The freezing point of bromine is. Now this is kind of a random question. However, you have the ability to answer it. Table S gives us all the melting and boiling points of all the elements on the periodic table. You have to remember that the melting and the boiling point is exactly the same value. In one, energy is being absorbed, and in the other, energy is being released. Because Table S gives us these values in the Kelvin scale, you would need to convert that value to Celsius. So, according to Table S, the melting point of bromine is 266 Kelvin. So Celsius equals 266 minus 273, or -7. A measurement of heat, or potential energy. The amount of heat lost or gained in a physical or chemical reaction can be calculated using the formula on Table T, Q equals mc delta T. You're given what all the variables mean. You're not given that Q is measured in joules. You do have to remember that. Mass is measured in grams, delta T in Kelvin or Celsius, and specific heat has units of joules per gram degree Celsius, which you can find in Table B. The specific heat capacity of a substance is the amount of heat needed to raise the temperature of a 1 gram sample 1 degree. So for example, we usually deal with water in our heat problems, and the specific heat capacity of water is 4.18 joules per gram degree Celsius, which can be found on Table B. All this tells us is that it takes 4.18 joules to raise 1 gram of water 1 degree Celsius. Here's an example. How much heat is needed to raise the temperature of 500 grams of water by 15 degrees? The first thing we want to do is write down our variables. Our mass is 500 grams. Our specific heat capacity of water is 4.18 joules per gram degrees Celsius, and our change in delta T is 15 degrees. Write down our formula, substitute in, and solve. Notice how grams and Celsius cancel, so my units are left in joules. Now I rounded this answer to 32,000. Please don't do that on the Regents. Write exactly what you get unless you're told otherwise. How much heat is needed to raise the temperature of 25 grams of water from 27 degrees to 47 degrees? So the first thing you want to do, write down your formula. You should write down your variables, which I didn't do. My 25 grams, my C is 4.18, and my change in temperature from 27 to 47 is 20 degrees. My grams and my Celsius cancel, leaving me with joules, and I get an answer of 2,090 joules. How many joules are absorbed when 50 grams of water are heated from 30.2 to 58.6 degrees Celsius? Q equals mc delta T. My mass is 50, my C is 4.18, and my delta T is 28.4. My Celsius and grams cancel, and I'm left with 5,935.6 joules. What is the specific heat of silver if a 93.9 gram sample cools, that should say from, 215 to 196 degrees Celsius with a loss of 428 joules of energy? Well, I'm solving for C. So I'm going to divide both sides by m delta T, and I see a mistake. It should say C equals Q divided by m delta T. There should be delta T here. So C equals 428 divided by 939.9 times 19 degrees Celsius. So my C is 0.239 or 0.24 joules per gram degree Celsius, which makes sense because none of my units canceled, and joules per gram degree Celsius are the units for specific heat capacity. In this problem, we're given 1,000 joules being added to 20 grams of water at 30 degrees Celsius. They want us to solve for the final temperature of the water. So I'm going to divide both sides by MC to get delta T by itself, and I'm left with delta T equals Q divided by MC. When I substitute in, I have 1,000, which is my Q, divided by 20 times 4.18. I get a delta T of 11.9 or 12 degrees Celsius. Now this is not my answer. This is only my change in temperature. They want to know what the final temperature of the water will be. Well, I go back to the beginning of the problem, and it said that I added 100 joules. Therefore, if I'm adding energy, my temperature is going to go up. So 30 plus 12 will give me 42 degrees Celsius. That's my final temperature. The law of conservation of energy tells us that energy cannot be created or destroyed, only converted from one form to another. In calorimetry, we can use the heat lost by one substance, and that should equal the heat gained by the other substance in a perfect world where no heat is lost to the environment. So essentially, your heat lost equals your heat gained. And since Q equals MC delta T, we could say that MC delta T lost equals MC delta T gained. This concept right here will be very important in our next upcoming lab. So if I have a calorimeter with hot water inside a metal can, and I put that inside a cup of cold water that's held in a styrofoam cup, initially my hot water has high kinetic energy because it's about 70 degrees, and my cold water has low kinetic energy because it's at about 5 degrees. However, if I let that sit, thermal equilibrium takes place, and the average kinetic energy and temperature of each sample of water will eventually be equal. Phases of matter. Let's review. Between solid and liquid, I can either melt or solidify, aka freeze. Between liquid and gas, I can either condense or vaporize, aka boiling. Between solid and gas, I can either sublime or I can go through deposition. Or showed you this example with the iodine crystals as a demo. Another good example of this is carbon dioxide, dry ice. It goes from a solid phase directly to a gas phase. And another example that was mentioned by someone in class was naphthalene, mothballs. This will end the first half of the review lesson.